Testing. Hello. Okay. Thing seems to work. Let's say. Okay. Good afternoon, everyone. Like I said, last time I recorded this session, we had a problem with audio. I think I fixed it. This chapter is about sampling distribution and hypothesis testing. So I decided to divide it into two, but now that we can't use the first part, I'm going to combine both of them. The first part is about sampling distribution, which is mostly research, a type of sampling and the factors of that surround sampling, and then hypothesis testing. So I'm going to combine them and we're going to go over them. Here it is, what we talked about so far. As you can see, what you're looking at, let me just make this a little more pleasant. Okay. What we're looking at is a normal distribution. And those squares represent a sample. In reality, we said we can take unlimited sample from a population. So if one of these squares is mean, then let's say the population is Albizu University, let's say with 1,000 students. If my sample contains 200 students, there's still 1,000 students in the population for others to research them. So there are unlimited sample. We can pull unlimited sample because we put them back once we use them. This, okay, so again, today we're gonna go over another Z-score. This Z-score is designed for sample. It opposed the one that we used before, which was used for one single score, or one or single score. So for that, we need to understand the concept of standard error. As you can see, that's the new symbol, is sigma m. In reality, a standard error, or the standard error of the distribution of sample, but standard error for short, is the standard is the standard deviation of the distribution of sample means, and it's called the standard error of the mean, or just standard error. So this means if we take unlimited sample from samples from the population, and of course we give our participants some kind of test, let's say depression test, and but since it's the Z-score, let's say some standardized test, because the depression is not a standardized test. Then we give them a score, we give them a test, and then each person get a score. And then each sample has a mean for each sample. Hypothetically, if these are our mean, I use single scores, so we won't have any problem with calculation. There, you see, we have 4 samples, and the mean for each sample of the scores of those participants is 8354, written in black. So with that, if you wanted to calculate the standard deviation for this, which is the square root of SS over N. So you calculate the SS like we did in the past, divided by total number, which is 4. This is the standard error, but it's kind of silly because nobody will do that. So for that, instead of all this, there is a formula just for standard error, sigma m. And instead of doing all that, this is just to understand what is the standard error. And when you conduct research, you want your standard error to be minimized, minimum, because it's error. You want the error in your research to be very low. So here's the formula for it at the bottom. A standard error is a standard deviation of your sample divided by square root of n sample size. So you can always read these slide in details, so I don't have to just read them. A standard error, that's the formula we just decide. You can write it this way: standard deviation of the sample divided by square root of n, or you can put this whole right side equation under the square root and come out with a variance, which is sigma square divided by n. Either way is same. And the other two at the bottom are derivatives of a standard error. You derive these formula from that. It's a little algebra. If you don't know algebra, it's okay. So if for your quiz exam, if I ask for, n, which is participants or number of scores, this is how you calculate it. Standard deviation, I give you standard deviation and a standard error, and then this is how you write it, and then the square of that. Or if I give you the standard error and sample size, then you'll be able to calculate the standard deviation using that formula. And here they are. That's what we talked about. Another thing we need to know is confidence interval, or CI. Confidence interval is opposite of alpha. Alpha is probability of what we found in our research is by pure chance. In other words, we were lucky. We reject the null. It was just the luck. So the higher the CI, the lower the alpha, or the opposite. So if in metric, if CI is 95%, alpha is 5% chance of error, or just finding it by chance alone, which in proportion will be 0.05, 5%, 0.05. Same as 99% if CI is. In social sciences, we use either CI of 99% or alpha of 0.01 or 0.05. And here's the description for the alpha. And there's a link that you can calculate the standard error. And we're going to use the SPSS momentarily to calculate that. And then we have effect size. Effect size, unlike the standard error, you want that to be large in your research, because effect size is when we reject the null, and it tells us how big the differences are. The difference between treatment group and treatment group or control group, treatment group or experimental group, and control group. The larger the differences, the larger the effect size. And there's a little table in your book. It says that if your D or Cohen's D that we use for Z-score greater than 0.8, then is a large effect. And we get to that in a moment. That's what we said. So this is how we do it, what we just discussed. If you go to SPSS, right there when it says variable view, type in mean or means, let's say means of the different sample, and you put your number. So here they are. Let's say we have 10 samples, and these are standardized tests, and for, let's say it doesn't matter how many people are in each sample, but the mean or average for each sample are right there under the means. So this is how we perform it. You go to analyze, you go to descriptive statistics, explore. Click on explore. You transfer your, right here in that red circle, it says means. All that data is attached to that word means. So it's here, you put it right there. You drag and paste it to means. And then you click on the statistics, and you click on descriptive, but here we're interested in the confidence interval. SPSS has a confidence interval of 95% by default. So you don't have to change it unless you wanted to switch to 99%. Again, we either use 99% or 95%. They are very popular in social sciences. Click continue, okay, and here you are. That's your standard error, shaded in black, 3.71. Also at the bottom, you see a stem and leaf plot that we talked about in the past. SPSS always generate more than what we ask. So, and then also it gives you a plot. We divide your means. It tells you what the highest means, the handle, the top handle. They tell you the highest means, it should be right there. This is like 55 or something. And the lowest, the lower handle, which is a little over 20, maybe 22. And then the middle, that thick black line in the middle of that rectangular is the middle score, the average. The law of large number simply tells you that the larger the number, the better. It's a better representative of the population. You use, we use either X bar or M to represent sample size. Depends on your textbook. I use M for sample size. And here in this graph, you can see the relationship between sample size and standard error. We said that standard error should be low in your research. So as you can see, the larger your sample size, the lower your standard error we get. And you see, if you move to the left, you see if your sample is that consists of 10 participants, your standard error is high. compared to 200, which is coming down low. So the formula that we used previously for the Z was Z equal X minus mu divided by standard deviation. This for Z for the whole purpose of Z score is we use Z score for when we use a standardized test in our research, whether single score, that formula, we already covered it, or for research, which you got to have more than one score. It's a little different, and we're going to go over it momentarily. And so here, if you have a research like this, it tells us that the Z score, okay, so it says short-sighted people are more intelligent. So with that, you need to have conduct research to find out. This is your hypothesis, your research topic, and you have to prove this. If you can, prove this hypothesis, test your hypothesis. So with that, you have to have a sample of participants. And you got two variables. One of them are short-sighted. So these people are, let's say, nearsighted, short-sighted. We know that. They already been tested by their eye doctor, ophthalmologist, and optometrician. Then somehow measure the intelligence when we use IQ test, which is a standardized test. So with that, let's say we have 100 participants, N is 100, and we give them IQ test, and the mean or average M for the sample size will be 110. And we know that mean for IQ is 100 and a standard deviation of 15. So this is how you do it. This is how you calculate the Z. First, you calculate the standard error at the bottom, which is a standard deviation divided by square root of N. So standard deviation for IQ is 15, and N is 100 participants. So 15 divided by square root of 100, 100 is 10. So 15 divided by 10 is 1.5. Once you determine that, that goes for denominator of the Z formula, the new Z formula. And then on numerator, top, you have a sample mean of 110 minus population mean, which is the mean for IQ. 110 minus 100 divided by 15, that gives you a Z score of 6.66. So for test hypothesis, this will be the step 3. When you calculate the Z score, you calculate the Z score, and at step 2, you need to find the critical value for the Z. Depends on your alpha and one tail or two tail. We're going to go over it shortly. So you compare these two. If the calculated Z, this Z, is greater than critical value of Z, critical value is the value that are on back of your book, and we already talked about them when we covered the Z for single score. If it's greater, then you fall into rejection zone. That means you reject the null. Null always say there's no difference, but we reject it, meaning there is a difference. There are differences. And we're going to go over that quickly. So here's the Z score, and these are the derivatives of the Z score for the test purposes. And that's, we already covered that. And the effect size, we talked about it. Needs to be reported. There are each chapter that we're going to cover this semester and in advanced statistics, I have a different effect size. But for z-score, we use Cohen's d. And then again, as you can see, for ANOVA, we use eta squared. For R, which is a correlation coefficient, or R squared, which is coefficient of determination. We use phi coefficient for Kramer's V, chi-square, okay, for that. When we get there, we talk more about this. This is more advanced stats. But for now, the only effect size you need to know is on top. It says Cohen's D. And it has a formula. And we're going to go over it in a second. So what's the minimum number of subjects for each group or each value or each variable? If it's a correlational or regression, you go by variables. So you got to have at least 30 participants for each variable. If you have groups, like two independent t-test or ANOVA, for example, then you need to have at least 30 participants for each group. Cohen's D, there it is. It tells you what it is. And this is the table we go by. If it's greater than 0.8 and greater, is large effect. If it's less than 0.8, but 0.5, but less than 0.8 is medium effect. If it's less than 0.5, but 0.2 or greater, but less than 0.5, that's a small effect. If it's less than 0.2, it's zero effect, no effect size. And that shows that like for example, you can see here treatment group and control group. If there's no difference, you only see one distribution. So, but you can see that dotted lines, that's the mean for each distribution. You can see two different mean. But if it's one, you only see one mean. But the larger the difference between the two means, the larger the effect size, which is good. That means the more power, statistical power, you have to reject the null. That's the meaning of it. So here's the formula for Cohen's D. Cohen's D is M minus mu, just like a z-score, but instead of the denominator for the z formula is a standard error, sigma m. But for Cohen's, the only difference is that is a standard deviation. And the other two are derivatives for Cohen's D. Like, for example, if I give you sample size and the Cohen's D, and then you know the population mean, if it's IQ 100, then I ask you calculate the standard deviation. Or the next one, calculate the sample mean. Again, I give you Cohen's D and the standard deviation, you multiply them plus mu, IQ, mean for population. Or if you wanted to calculate the mean for population, then sample mean minus Cohen's D times, or D times standard deviation, Cohen's D times the standard deviation, M minus that, whatever you get. So when it comes to hypothesis testing, this section is very important because from now on, we're going to keep covering the same stuff. Whatever the statistic is, but we talk the same hypothesis testing apply for all test the statistics, whether it's Z-score or t-test or ANOVA, correlation, regression. It's always, so it's better to learn it right away now as opposed to just wait. You can always let me know if you have any problem, anything. And keep in mind that we're getting close to midterm. And after this one, you'll be ready to take your midterm exam. I will email everyone and let you know. Here's the logic behind the hypothesis testing. You can read it. And there's a null hypothesis that you can see here illustrated in green. And H1. H1 is the researcher hypothesis or alternative hypothesis. Some texts have it as HA, it's the same thing. But H0 or H0, that's null hypothesis. Null is an entity that you always have to deal with in research. Whatever your hypothesis is, whether you're looking for difference between the groups or correlation, regression, null always says, I don't think so. If you say it's same, there's no difference, null said there is difference. If you say there's positive correlation, null says negative correlation or zero correlation. So you gotta deal with that, with those hypothesis testing, if you can, to either reject the null or retain the null, or if you can, you fail to reject the null. Either way, you're going to find out something about your research. It's not like, if you reject the null, that means yes, you got a point. If not, still you found out that according to your data don't support. They refute your hypothesis. Your data refute your hypothesis. So here they are, null hypothesis, H1, right? And then alternative hypothesis is the researcher. In terms of hypothesis testing, you need to know that there are, so step one in hypothesis testing is always the same, as you can see. Null always says there's no difference, and state the hypothesis. We, the researcher, H1 or HA, alternative hypothesis, we say there are. That's the topic. That's the hypothesis we want to test. We say there's something there. That nada, that's zero, means no difference, no correlation. But we think there are differences or differences. So it depends on what kind of hypothesis you're using, one tail or two tail. Well, step two is locate the critical regions. It depends on if you're using one tail or two tail hypothesis. One tail tests are called directional. Whether on the tail is on, that means the alpha that I mentioned earlier is either on the right tail, like highlighted in dark blue, or the left. And right there, it tells you for the alpha being 0.05, one tail, that's 5%. It says right there in that square. The Z value, if you go look at the critical value for the Z, you will see that the Z value with alpha in tail will be 1.645. And then again, whether it doesn't matter whether the tail is on the right side or the left side. It'll be the same because they mirror image with alpha 0.05. Either one. So, okay. But if you use two-tail tests are better, meaning they are more accurate. In this case, the alpha will split, and 0.05 will be divided to 2, and you have 0.025 on each tail. The critical values that you look, like 1.96 will be the value for the Z if it's on the right side, and on the left will be negative. It depends on the hypothesis. If you say that on your hypothesis, like the one I just showed you, if you say short-sighted people have a higher IQ, this is a one-tail hypothesis because you're clearly indicating that on the right side, higher IQ. Or on the same token, you say short-sighted people have a low IQ. So it still is a directional one-tail hypothesis. You're saying left, they have a low IQ. But if you don't want it to say, you just say, something about, let's say, the effect of nearsightedness on IQ. You don't know. You're not saying it's more high or low. So with that, you cover in both tail. Once you calculate the Z, then if the Z come out on positive, then you're on the right tail. If it's negative, you're on the left tail. And if the Z, the calculated T, is greater than, let's say, 1.96 in this case, if alpha is 0.05, which is okay on each tail. If it's greater, the Z, then falls into red zone, which is rejection zone. So I mentioned T. So for the T test, which we're going to cover after midterm, it's the same. It's the same principle, except instead of Z, critical value, we got to look at critical value for the T. All right. So there's our values. You calculate the T. So step 1, state the hypothesis. No say no difference. We say there are difference. Step 2, find the critical region by knowing what is you're using one tail or two tail test, and what is your alpha, 0.05 or 0.01. Step 3, you calculate a Z as I demonstrated earlier. Step 3, and step 4, you make decision. So this is your normal distribution for the Z with the mean of 0. And again, with alpha, one tail, 1.645, that's the Z value. So if you're critical, like the one we calculated earlier, if you go back the video, we calculated Z was right there is 6.66. So 6.66, the decision will be right there. Is the red zone or rejection zone start with 1.6, so 6 will goes to the right, and somewhere in the end of that distribution, the tail of that distribution falls in there. Any number greater than 1.645, 1.645 or greater will fall into the rejection zone. So the decision will be reject or no. However, if our calculated Z is less than 1.645, even if it's 1.644, you know, like that red dot red line I put in there, that look like 1. If it's there in a white area, then we fail to reject a node. Well, we have to accept a node, fail to reject. So that's how it is. All right, so there it is. So all the formula for tonight, again, it says for your information, the z-score right there, that's the formula for the z-score. Degrees of freedom, n-1. If I give you the degrees of freedom, and that right there on top left side of the screen, ask you what is sample size, just add 1 to degrees of freedom. Degrees of freedom is n-1. The formula for the z, n minus mu divided by standard error, and those are the derivatives. 2, 3, 4. And then Cohen's d, if you ask to calculate that, is n minus mu divided by standard deviation, and those are in purple, and those 2, 3, and 4 are derivatives. And for hypothesis testing, is right there, and then on top blue, how to calculate the standard error, either those two formula. You calculate it, then you put it right there in the z-score on the left in blue. So for hypothesis testing, step 1, once again, node says no difference. Researcher says there's difference. Step 2, you find the critical region by looking at, I'll show you in a second, back of your book like we did last time. Step 3, calculate. Right there, we calculate this was 6.66 and make a decision. So if it falls into the region or beyond, we reject, rejection zone. If it falls short, we retain. So again, if alpha is 0.05, one tail, so alpha 0.05, that means that right there, that means you're in a tail. Tail means a smaller portion. If it's 0.05, this is back of your book, critical value for the Z. We're looking for a smaller portion, 0.05 in proportion. Right there, right when it says alpha. Now let's go back. 0.05, right there. On the left side of the screen, I underline it in blue. A small portion, that's alpha 0.05. That's the closest you can get. So if you move to the left, you see that z-score is 1.65 or 1.64. Not much difference. But, okay, the closest, you could use either one of them. The underline is 5 over, would be 1.64. And the one underneath 1.65. Either one is correct. And then these are, again, we already covered those. So again, these are the problems that you should be able to, right there it says with description how to do this. You calculate the z-score, and then once you've done that, then you look for the proportion and convert into percentage. Let me know. You do this and you send them to me. You get extra point for your midterm. And for second half of the semester, we do the same thing. And then here illustrated that what they're looking for, but most of these problems, they really want a standard error, stuff that we talked about, standard deviation. So yeah, again, it depends. Be careful what they asking, whether they're asking for a standard deviation like this one or a standard error. That's one thing you need to be careful. Try them. Again, if you had any problem, let me know which one you got it there. You should be able to, once you feel comfortable with this, you should be able to take that quiz and you're ready for the midterm. All right. And this one, it says z-score less than 1.5. So if it's 1.5, less means the left. So that's the large section or body. You go look for a z-score of 1.5, and then again you gotta look for we already talked about these in the previous chapter. Large section, that would be the answer. There's no formula. All right, so that's a sample research. Okay, so please take the next quiz. I believe it's 4, and do all your assignments 4 and 5. Next time we will cover t-test. So again, we're not going to meet next time or next, because we're done with this. The next chapter we're going to cover will be t-test. So you got 2 weeks basically to do all your SPSS assignments and take all your quizzes. Most of you already done that. I appreciate it. I appreciate your motivation. I consider myself lucky that this year I have a really good students. All of you are really doing a great job. Okay, so let me know, please, if you have any question, concern, and I'll be more than happy to help you. So again, you should be able to take your midterm exam. With that, you'll be done with the first half of semester. And check your grades, and you have your SPSS. You shouldn't be worried about anything. You cover everything. You should be. Keep in mind that you have 2 attempts for your midterm exam, as well as your quizzes. So the first time you're not happy, take it again. Have a great day, and the next lecture will be about 2 weeks from now or so. I will continue communicating with you via email. All right.